Okay, folks, if you've chose this problem, you've chosen one of the hardest problems there is to do for optimization in calculus. So, what I want you to do is I want you to read a quick sentence about it and try to draw a diagram showing a sphere with a cylinder inscribed inside of it. So, let's first see if you can figure that out, what the picture would look like, and then we'll come back and compare answers. Okay, well, here we have a cylinder inscribed inside of the sphere. What we want you to do is try to come up with the intersecting geometry. What I mean by that is overlapping segments between one figure and the other. For example, how would the radius be drawn that would represent a quantity for both the cylinder and for the sphere? See if you can draw that segment into the diagram, and then we'll work from there. Now think of some other dimensions that are relevant to the sphere. To the cylinder. If you look at the sphere, there's only one dimension relevant to the sphere, and that would be the radius equaling 10. But what dimensions are relevant to the cylinder? Remember, the volume of a cylinder is equal to pi radius of the cylinder squared times the height. So we don't have any dimensions on this figure yet that relate the radius of the cylinder and the height to that of the sphere. So let's try to set up some of those equations or label those parameters on the picture. Okay, so I've made a choice here. Maybe you've made some similar choices. I put down what the formula for the volume of a cylinder is, and I also made a choice to make my life easier to name the radius just the variable x, because I don't want to confuse it with the radius of the actual sphere. And I have the height of the cylinder also as another dimension, just as h. But what we want to do is we want to try to consolidate some of these variables. And I see that I have a certain relationship showing up here where I can relate the radius of the sphere to the radius of the cylinder to half of the height of the cylinder. So what I want you to do is come up with a relationship that relates x to y to the radius of the sphere, and let's see if we can replace some of these equations. So what I've decided to do was I replaced the height with 2 times the value of y, because I realized that if I'm going to switch the radius to x, I want to switch the height to also something to do with y. So twice the height is equal to, twice the y value is equal to the height, and now I can use Pythagorean theorem to put y in terms of x. So I wrote out Pythagorean theorem, y squared plus x squared equals the radius squared, and I solved for y as a function of x. And now I'm going to plug that into my volume equation, which I'm going to try to maximize. As we said before, people, when we come up with a volume function, or when we come up with our optimization function, sometimes it's good to just plot it to see if we can find a maximum value for that. So I would like you to take this function, and let's just put the 2 up in front. Volume equals 2 pi x squared times the square root of 100 minus x squared, and plot this plot the volume against the values of x in an appropriate window, and look for where you can find the maximum volume and what the dimensions would be for x. So I plotted the volume as a function of x, and we definitely have a maximum value occurring. And when I solve for the maximum value using the graphing calculator, I got 8.16. I'm forgetting the units, so let me just look back. 8.16 centimeters for where that max is. And the volume that I got from that, let me look back at the calculator. If I do a trace on, I type in 8.16, it says that the volume is about 2,418 centimeters cubed. What I'd like you to do is take this volume equation and take the derivative of it and solve for the critical points, and let's verify that we get the same answer. So I'm going to work on that on this line paper. You can see I've gotten organized, and I'm going to work through that. There's a little bit of a product rule going on and chain rule and all that good stuff, and then we've got to solve for the critical points. So let's see if we can find that value that we got for that critical point and that value for that volume. And that would conclude our exercise with this volume equation. Well, if you've completed this task, you should have found that the critical point algebraically is equal to 10 square root of 2 over 3. If you plug that back into the equation over here, you should find out that your y value is equal to the square root of 100 minus, now you've got a squared 10 square root of 2 over root 3, which will be the square root of 100 minus 200 over 3, because this has to be squared, which is 100 over 3 square root. So that would be your height. Half of your height, actually, because this y value only represents half your height. So remember, you're going to have to double that. So your height will really be, if I bring the 10 out of the radical, it will really be 20 over root 3 should be your height. Well, when you plug this value in, it turns out to be 8.16, and if you want to look at the calculus, you could look at how we took a product rule to get these two parts, and then we combine denominators, and then we simplify the numerator in this step, and then in this step we set the numerator equal to 0 and the denominator equals 0 to get our critical points. And this point here and this point here is just the case where we're at our extreme values for the domain, and if we plug in 0 for x or 10 for x, we end up having a 0 volume. And this value is we have a plus or minus value. That is a value that gives us the critical point that yields the maximum value for volume. I hope this video was as fun for you as it was for me, but this was some really complicated calculus to get through in a quick amount of time. So please look over the solution, the calculus solution, and see if you can understand what went on in the differentiation process, and let me know your comments.